Rust ownership is one of the biggest reasons beginners get stuck. In this video, we will solve 14 practical challenges that show exactly how ownership, borrowing, and mutable references work in real code. By the end, borrow checker errors will start to feel like useful feedback instead of random failure. We start with the rules. Every Rust interview expects you to know who owns a value, when a value moves, and when borrowing is the better choice. This comes up when user input is sent into a helper function, but the caller still needs it later. Let's write the tempting version first. The function takes a string, so calling it moves the input. Now we run it and the compiler stops us because we try to print input after ownership has already moved. Let's break down the error. A string owns heap memory, so Rust will not silently duplicate it after input is passed into process input. Main no longer owns that string and using it again would be unsafe. Now we fix the design. The helper only reads the text, so it should accept a string slice instead of owning the string. We pass a reference, run the program again, and now the original value is still available in main. The best option here is borrowing because the function only needs read access. Use ownership transfer when the function should store, consume, or permanently take responsibility for the value. For simple processing, a reference keeps the caller flexible. For practice, rewrite this so process input really does take ownership. Return a tuple with the original string and the processed message. That forces you to think about how ownership can be passed back explicitly. Imagine an inventory system where we keep a product name but also send it to logging. First, the integer count is copied because small numeric types implement copy. Then we clone the string for a function that owns it. And finally, we borrow the same product name for a read-only logger. Now we run it and compare the output. Let's read the result carefully. The count works on both sides because copying an integer is trivial. The product name needs a clone only when we require a separate owned string. But the borrowed logger can read the same data without making a duplicate. Now we simplify the design. A logger usually does not need to own the product name, so we accept a string slice. We run this version and keep ownership in the inventory code the whole time. The best option is to borrow first and clone only when a real independent owner is needed. Cloning is explicit in Rust because it can allocate memory and cost time. That makes performance decisions visible in code reviews and interviews. For practice, create an inventory vector and decide where clone is truly needed. Push a product name into the vector, then log it by reference. The goal is to clone for storage, not for simple reading. Next, we use shared references for validation. The goal is to inspect data without taking it away from the caller. Email validation is a perfect example of read-only access. We only need to inspect the text before storing it, so the function takes a string slice. Now we run it and confirm that validation works while the original email is still available. Let's break down why this is the right shape. The function does not store the email and does not modify it. So ownership does not need to move. Multiple parts of the program can read through shared references as long as nobody is mutating the same value at the same time. The best function signature here uses str not string. That makes the function more flexible because it accepts a string reference and also a string literal. In interviews, this is a small detail that shows you understand Rust API design. For practice, make the validation a little stricter. Reject values that start with an @ or end with a dot. Keep the same str signature so ownership behavior stays clean. Now we move from reading data to updating it in place. Mutable borrowing gives temporary write access without transferring ownership. Before saving a username, we often need to trim whitespace and apply consistent casing. Here, main owns the string, and the helper gets a mutable borrow just long enough to update it. Now we run it, and the terminal shows the cleaned username. Let's unpack the update. The function cannot keep the reference forever. It only borrows username during the call. After the function returns, main can use the updated string normally. The best pattern is to use a mutable reference when one function needs short-lived write access. This avoids returning the whole string just to hand it back. It also makes the mutation visible at the call site because you must write mut. For practice, extend the normalizer, so internal spaces become underscores. Keep the function in place and keep the same mutable reference signature. That gives you another small mutation without changing ownership. This section focuses on the rule that prevents data races, one mutable borrow at a time for the same value. Account balance updates are a realistic place to hit this rule. The mistake is creating two mutable references to the same balance before either one is finished. We run this version and Rust rejects it because exclusive access would no longer be exclusive. Let's break down the compiler message. Deposit still exists when fee is created, so Rust sees two active mutable references to balance. That could allow conflicting writes, so the borrow checker blocks it at compile time. Now we fix it by making each mutable borrow short. The deposit reference exists only inside the first block. Then it ends before the fee reference is created. We run the fixed code and get one final balance after both updates. The best habit is to keep mutable references alive for the shortest useful time. If you only need to perform an update, do the update and let the reference go. In larger code, this often means using smaller scopes or helper functions. For practice, replace both blocks with a small apply change function. It should take mute i32 and an amount, then apply the update. Calling that function twice is a clean way to avoid long-lived mutable references. In this section, we practice the rule that makes Rust references safe. You can read through shared references, or you can mutate through one exclusive reference, but you cannot mix active shared reads with mutation. Imagine a shopping cart where we need to print the current total and then apply a discount. We write the total calculation inside a short block so that read-only access ends before the mutable loop starts. Now we run it and check that both operations happen in order. Let's break down why this works. The iterator borrows prices immutably only while we calculate and print the total. Once that block is over, there is no active shared borrow, so Rust allows the mutable borrow in the loop. Now we show the best habit for this situation. Keep borrows as short as the real job requires. Use a small block, a helper function, or a temporary value so the compiler can clearly see when reading ends and mutation begins. Try a small variation yourself. Add a fourth price. Change the discount amount, and make sure the program still prints the original total before it mutates the vector. This section focuses on return values. The key interview idea is simple. A function cannot return a reference to data that dies when the function ends. A common interview trap is generating a temporary value inside a function and trying to return a reference to it. Here, the token belongs to generate token, but we return a reference now. We run it and Rust stops us because the reference would point to data that is already gone. Let's explain the failure. The string is created inside the function, so it is dropped at the end of that function. A reference to that string cannot be returned because the caller would receive a pointer to invalid memory. Now we fix the function by returning string instead of a reference. This moves ownership of the token out to the caller, which is exactly what we want for newly created data. Now we run it again and the token prints normally. The best approach here is to return an owned value when the function creates the data. Borrowing is great when the caller already owns the data, but generated data usually needs to be moved back to the caller. Try this variation next. Accept a user ID as input, create a token with format, and still return an owned string from the helper. Here we use explicit lifetimes only where they add useful information. The goal is to connect a returned reference to the input references it may come from. In a UI or product system, you might choose the longer display label between a product name and a fallback label. We implement longest with one lifetime parameter because the return value can be either input, now we run it and see which label is selected. Let's break down the annotation. The lifetime name does not make anything live longer. It tells Rust that the returned slice is tied to the same valid lifetime as the input slices used in this call. The best way to use lifetimes is to describe relationships, not to add them everywhere. In this case, the annotation is useful because the compiler needs to know the output comes from one of the two inputs. Try changing monitor to ultra-wide monitor and run the same function again. The goal is to confirm that the lifetime annotation stays the same even when the branch result changes. This section shows how Rust can borrow independent struct fields separately. That matters when one field is only read while another field is updated. For an audit log, we want the user's name for the message, and we also want to increment the login counter. We borrow only the name field, then mutate only the login count field. Now we run it and confirm the counter is updated. Let's look at the important detail. The reference is not to the whole user object, it is only to the name field. Since the mutation changes a different field, Rust can allow both operations safely. The best pattern is to borrow the smallest piece of data that the operation actually needs. This keeps the rest of the struct available and prevents unnecessary borrow checker conflicts. Try adding an email field to the struct, borrow the name and email for the audit text, then update only login count and print the final line. This section is about API design. When a function only needs to read a sequence, accepting a slice makes the function more flexible than accepting an owned vec. Suppose we track recent metrics in a vector, but our average function should work with all values or only part of them. We accept, which means borrowed read-only access to a sequence of integers. Now we run it and compare the full average with the recent average. Let's break down the result. The full slice contains 10, 20, 30, and 40, so the average is 25. The partial slice starts at index 2, so it contains 30 and 40, and the average is 35. The best API here is a slice parameter because the function only needs sequential read access. Use vec in the parameter only when the function must own, store, or resize the collection. Try one more slice challenge, add a fifth metric, calculate the average of the last 3 values, and print it with 1 decimal place. Now we move into collection, borrowing problems. These are common in interviews because they look simple, but they quickly expose whether you understand how iterators borrow a vec. Imagine we are scanning overdue tasks and adding a follow-up task for each match. This first version looks natural, so let's write it and run it. The loop borrows the vec through iter, and then we try to push into that same vec while the borrow is still active. Now we fix it by separating reading from writing. While we iterate, we only build a second vec with the new tasks. After the iterator is done, we extend the original vec and then look at the output. Let's break down why the fixed version compiles during the loop. Tasks is only immutably borrowed, so reading is fine. The mutable change happens later after that borrow has ended. The best practice here is to treat iteration and structural mutation as 2 separate phases. Use a temporary vec indexes or iterator adapters that produce a new collection. This keeps ownership simple and avoids hidden reallocation problems. For practice, adjust this example so every invoice task creates a review task. Keep the same pattern. Scan first, store new values separately, and extend only after the loop. Next, we look at closures. This matters because closures can borrow, mutably borrow, or take ownership, and threads usually need owned values. Here's a realistic case. We preview a config locally, then start a background worker with its own config value. The first closure can borrow because it runs right away. For the thread, we use move and then run the program to confirm the thread owns what it prints. Let's unpack what Rust did here. A closure chooses the least powerful capture mode that works: immutable borrow, mutable borrow, or ownership. A spawned thread may outlive the current stack frame, so move makes the captured string live inside the closure. The best practice is to use move closures for threads and async work when captured data must outlive the current function. This makes ownership explicit at the boundary where work leaves the current stack frame. For practice, create 2 worker configs and spawn 2 threads. Give each thread its own moved string, then join both handles so main waits for both jobs. Now we use shared ownership. This is the right tool when several parts of a single-threaded program need to own the same read-only data. Suppose 2 services need the same application config. Instead of cloning the whole string, we wrap it in RC and clone the RC handle. Now we run it and watch the reference count change as owners enter and leave scope. Let's make the important part explicit. RC clone does not duplicate the config text. It creates another pointer to the same value and increments the strong count. The best practice is to use RC when you need shared ownership in one thread. If you only need to pass temporary access, use references instead. RC is for ownership, not just convenience. For practice, add a third service called analytics inside the inner scope. Before running it, predict the count inside the scope and the count after the scope ends. Finally, we combine shared ownership with controlled mutation. This pattern is powerful, but it moves borrow checking from compile time to runtime. Think of 2 UI components updating the same in-memory counter. RC lets both components own the counter handle, and refcell lets each one mutate the value when needed. We keep each mutable borrow short, then run it and check the final value. Now let's force the mistake interviewers often ask about. Refcell allows the code to compile, but if we try to hold 2 mutable borrows at the same time, the program panics at runtime. Let's break down the successful version. RC solves the ownership problem because several places can hold the same counter. RefCell solves the mutation problem, but only as long as the runtime borrow rules are respected. The best practice is to keep RefCell borrow scopes short and obvious. Use it when the compiler cannot express your ownership shape cleanly, not as a default way to avoid borrowing rules. For practice, add a reset function that sets the counter to 0. Make sure the mutable borrow happens inside the function and ends before you print the counter again. Now you have practiced the core ownership and borrowing patterns that appear again and again in Rust. If this helped, like the video, subscribe to Dev Level Up, and write in the comments what Rust topic or challenge set you want next.